Hi, I'm Mike with StarFire Engineer. This video will cover why we got into resin testing, what that means for you, what advantage you're going to get out of it, how we're going to do resin testing, and all the different things we want to learn from those tests. And specifically today, we're going to do a deep dive into the tensile test. We're going to look at what that is, what kinds of things we learned from it, why it's the base of basically all engineering materials of property testing. Stay tuned. If you're watching this video, chances are you have your own 3D printer or you're thinking about getting one. DLP or digital light process printers are super awesome. There's a couple that are really popular on Amazon right now. I personally am using an Anycubic Photon S. Martin, say hi, Martin. Okay. And Mark, another contributor here at StarFire Engineer, is using an Elegoo Mars. Hellstrom, say hi. These are really cool printers. You can do practically anything with them. If you can get an STL file or you can make one any shape, you can do it, and the resolution is awesome. There's all sorts of different materials to pick from, lots of cool things happening. You're gonna get to the point though, if you haven't already, where you're gonna print something, the STL file is perfect, you supported it perfect, it printed wonderful, no errors, and then you have this object you needed and it fails because the material properties itself failed you. Now, I ran into this early on when I was trying to make some PPE for the COVID virus stuff, and basically it was an easier way to wear a mask. Okay, a lot of people were doing that. The maker community was huge into supporting our first line protectors on that one. Cool ideas. So I made one, I designed one, I made one, and the material I was using was just way too brittle. And it was really hard to find out, wait a minute, like what material should we be using for this? So that is basically where the seed of this idea came from, is we want to be able to make a database of all these resins and what they can do for you. One question is like, Mike, why don't you just tell us the perfect resin? There really isn't a super resin. If I find one, I'll let you know. But just like we don't build houses out of steel or cars out of wood, in general, you're going to pick the right property for the right project. And that's really where we're focused on. So if you need something flexible, if you need something rigid, if you need something transparent, if you need something that cures fast, we're going to delve into all of those things and try to define the perfect situation for you. We're going to give you the tools to make that happen. Our first test is going to be the tensile test. Tensile isn't a word everybody uses. It's just pulling something in tension until it breaks. Same thing. So the first thing we usually do is we design a particular sample. We're going to start with steel because that's kind of a common base to start with, where you're going to understand that the best. So for when we test steel, you design a sample that has a neck down area of a known diameter or cross-sectional area. And then there's also a known length of that thinner portion. So we can really identify, as we're pulling this in tension, what's happening in there, and we can watch and measure everything that happens, and then we can learn so much from that test. Another thing you do in order to make it so that your test sample doesn't fail early is you polish it. So there's no roughness. Basically, roughness is lots of tiny little scratches and cracks, and those could cause premature failure. So you polish the sample, and then you place that sample into basically a hydraulic press, but we're going to pull on it in tension. As we're pulling on it, that sample is going to thin out and elongate. And we can measure that distance as that's happening. And then also we identify the force that we're putting into that, as we're stretching it. So we know at any given point how much it's elongated and how much force it's taken to get it that far. Then as the test sample is stretched farther and farther, eventually it gets to the point where it yields. At some point of molecular weakness, it starts to neck down at a specific spot, and you'll see that happen. And then as that's necking down, a process internally to the metal structure, and this is something cool in metals, is it'll actually work harden. So you have one point that's getting smaller and smaller in diameter very quickly, but it's also getting stronger. So at some point, then that necking down will get so thin that even though it's getting stronger, it can't compensate for that really small diameter, and then pop, it breaks. Then we're done with the test. Samples failed. Remember earlier I said we were going to learn a lot of things from this one test? Well, the best way to look at all of those things we're learning from the test is to graph it out. So let's look at our graph. We're going to measure the elongation, will be on the bottom axis, and then the force we're applying to get that change in length will be vertical. And as we start to measure that, you can see that the first section of the graph is very linear. So as we add force, the proportion of it is going to grow in length, and that's happening very smoothly. We get up to a point where it does that neck down, where it's starting to fail, and the curve sharply turns over, and then that work hardening takes effect, and it starts to get stronger, and it will actually hold more. So you can see that force part of the curve again going up. And then at some point it will start to fail completely, and it will curve off and be done. It'll break. Now our graph is complete and it looks pretty good, but it's only good for our one sample because we're measuring the change in length or the force we applied to it. If we put a different sample in there that it was a different size, or let's say we want to know how much a bolt is going to take before it fails, that bolt is different shape. So we can make this generic, and this is headed towards what in engineering we call a stress-strain curve. So instead of force, if we take that force and we divide it by the cross-sectional area of our sample, that is stress. It's represented in units of force per units of area. For us, I like using PSI. You can think that's the same unit we use for pressure. It's the same unit that we use for a lot of things. So if you think about that stress as the internal pressure that's trying to pull that sample apart, that's perfect. Now, strain is kind of a weird word because we don't really use it in common language. But basically, that's a ratio of that elongation. So if we take the amount that it is changed and divide by the original length, so let's say the original length was 2 inches, then if it moves 1/8 of an inch, then you can do that math and you can know how much strain it's under. That's really useful to us because now that stress-strain curve we can use for anything. If we go back to that bolt, we know how the diameter of the bolt, we know the length of the bolt. We can use that information, it's just math, and we can totally own what that bolt is going to react to and know when it's going to fail. Really cool. So now we have a stress-strain curve. Okay, let's look at our points of interest for our graph. I should say for some engineers that are watching this, you'll recognize that I've simplified things a bit. We're going to look at the yield point, but there's actually an upper yield point and a lower yield point, and the graph in that area is a little bit more complicated, a little bit more noisy. For our intended purposes, this is fine. However, if you came to this because some search engine told you that this is a great video about tensile test, great. I think you're going to learn a lot, but just know that you can look at a few other resources once you're done here, and you can study that upper and lower yield point and learn just a little bit more. But for resin testing, that's beyond our scope, so we're going to dive in with what we have. Now that first section is elastic. It's stretching And actually, if we took the force off, it would go back to its original size. So just like a spring, you could stretch it, and if you let go, it'll go back. So up, as long as that curve is linear, we are in that elastic range. And the strain that's existing in that, or remember, strain is that change in dimension per original unit area. As long as that strain is happening in that section, it is called elastic strain, in that it can give itself back. So again, if we remove the force, it'll go back to its original size and shape. All good. Now at the top of that is the proportional limit. So everything's proportional until the proportional limit. That makes sense. And up until that, it's completely reversible. And then you get to the yield point. And we're just going to have one yield point. That's okay. So we have our yield strength at that point. So that's the first kind of strength that we want to look at. Because up until you get there, again, it's reversible. So if you want to, like if you're designing a bridge or something that is going to see a lot of stress, but you don't ever want it to yield, you want it to always be good, then you're going to want to make sure that it's much lower than that yield point, that you never get to the point where it yields. So that's our yield strength. You'll often see that as a capital S, small y, yield strength. Now, after that, we get to the ultimate strength. So it will start to neck down, and it'll do that work hardening bit that we talked about. And at some point, it gets to, I can't hold any more. And that is the ultimate strength. And a lot of times you'll see that represented capital S, small u. And that's the point at which beyond there is no return, because it's basically failed at that point. Yeah, the curve will draw itself out a little bit more, but even if you remove the force at that point, it's still gone. It's just catastrophic failure. So that's our ultimate strength. But wait, there's more. There's still a lot more we can learn from this. The first one we're going to look at is the modulus of elasticity. That's basically the slope of that first straight section of the curve. So how much stress it will take to give it a certain amount of strain. And that tells us there's a lot of engineering formulas that use the modulus of elasticity, also called Young's modulus. And what that tells us, it's a really good number to understand, because if you're comparing one material to another, that basically tells you how well that product or that material will resist changing shape if you put it under a certain amount of stress or a certain amount of force. So as you can imagine, if you look at our slope on that, if a higher slope is going to mean it takes more force or more stress to move it the same amount, a really low Young's modulus or modulus of elasticity is going to mean that it doesn't take very much stress to change the shape quickly. So a higher modulus of elasticity is going to mean that it's basically more rigid, that it's going to yield slower. Another thing that we can do is if we take that curve and we look at that point up until the yield strength, and we then calculate the area underneath that curve, that number we get, basically the area under that curve, we can call resilience, which is really cool, because that's a way, when you're talking about how resilient a material is, well, in the engineering world, we can actually put a number to that. So as we test resins, now we'll have a number that represents its resilience, and you'll know what that means. See, this is why this first video is so important. Now, if we take that whole entire curve and we calculate the area under the whole entire curve, that we define as toughness. So we'll also share a toughness value for each resin. And that tells you basically this is the most this material can experience until complete and utter failure. So the tougher a resin is, the more it is willing, the more it's going to take before it fails. And that will be a really cool number too, to compare one resin to another. So not only do we have a yield strength for our resins that we'll share, we have an ultimate strength, we have the modulus of elasticity, we have the resilience of our resin, and we have the toughness of our resin. So we've learned 5 things from one test. That's pretty cool. But Mike, wait, you've been talking about steel this whole time, and I believe that you originally said we're here for resin. Correct. So we're going to end up testing 3D resin, and we're going to see what happens there. And do expect it to behave the same? Not quite. So let's talk about how we would expect different things to behave under a tensile test, because we're still going to learn these similar things. A brittle material might still have some sort of elastic range, but it's going to get to a point where instead of yielding, it's just going to break. So there's going to be catastrophic failure after a short length of elastic range. Plastics are usually something that as you go along the curve, it has what we call a 1% offset, in that if you stress it so far that when you bring the stress off, it's not going to go back to its original shape. It's going to be offset by 1% of whatever that strain was. So if you look at that curve, hopefully you'll be able to identify down at the bottom, at the base of the curve, some sort of straight or elastic, short elastic region. And you pick that as your slope, and then you follow the curve up to the point where you're going to study it. And as you take that stress off, then you use that original slope and you come back down to the strain line, and that is your offset. That is the amount that you've permanently deformed your sample, which is important for us to know how well the material will hold, and if there is some sort of offset, what is that? And we can compare resin to resin and we can see what that is. And again, these graphs are going to be a really awesome way to show that, because you'll see obviously in the graph something that curves over very sharply is going to have a wide offset. You're going to put a little bit of force, a little bit of stress on it, and it's never going to get back to that shape. Or something that curves over very slowly and is mostly straight is going to be very resilient, and it's going to return to very close to its original shape. Now, for our resins, do I think it will act like that? I'm hoping, and I think we'll show this, that there is some sort of elastic range early on. And I can say that because, I have designed a spring and I've printed it out, and this isn't fully cured, so it's just out of the printer, but I can stress it and it will return to its original shape. And actually this guy, the reason we did this is we're going to study how curing changes its resilience over time, and that's what he's for. So that's a little further down the road. The sort of sample we're talking about right now, this is, I'll hold it over my shirt so you can kind of see it. This is our tension sample, our tensile test. The official version is going to be a little bit different than this, and we'll talk about that in the next video when we actually do the tension test. There we go. So what's the next step? The next step is to do the tensile test for 3 different resins. I have 3 different resins on hand. We're going to start with those. We'll see what we get. There's an Elegoo Standard Gray, an Elegoo Washable, and then I also have the Anycubic Translucent Green that came with my machine. So we'll do all 3 of those. We'll have that data. We'll put it up on our website. By the way, the website is StarFireEngineer.com. Feel free to stop by and check us out, see what data we have. We should have the data up there for these first tests very soon. Along with anything else that we learned about resins, we'll share with you, and I'll have a permanent linked page that as we start to build up this data, we'll just grow that page and we'll always be able to return back to it. So that's the plan. You've made it all the way to the end of our video. So obviously you think you've learned something, maybe? Enjoyed yourself? Awesome. I hope so. If you have any comments, any ideas you want to share, please do so down below. If you want to make sure to see our future videos as they come out, subscribe, hit the bell. If you liked it, click like. That'll help us out. And again, we're really interested in helping you out as a maker, as the maker community. what information do you want to see? What test do you want to see? We want to make sure that we're helping you out. So thanks for watching. Let us know what you need. See you next time.